Okay, good morning, everybody. We're going to try and start on time today, and we're very pleased to have Jim McWilliams from UCLA as our first speaker.
Okay. This is a scale diagram, schematically, for the atmosphere, for the ocean, for other planets. Starting with on the planetary scale, where there are global circulations with global forcing, and continuing down in scale until the effects of molecular viscosity and diffusion effect dissipation. And if we think of it as a regime diagram, then the larger scales are on Earth small Rossby number, small Froude number, strong rotational and stratification control, geostrophic hydrostatic, call it geostrophic turbulence, insofar as the persistent circulations have instabilities to geostrophic eddies. And on the small scale, I haven't heard anyone contradict Kolmogorov universality for a long time. And somehow they do contradict. I haven't heard anyone else contradict Kolmogorov. Not today. You wanted to have the wrong reading. And somehow there has to be a connection, planetary forcing, microscale dissipation. And there is essentially a dilemma that has been presented ever since Charney articulated the theory of geostrophic turbulence, which is that after a certain amount of rearrangement in vertical and horizontal scales and rotating stratified flows, the net transfer of energy is inverse towards larger scales. That's away from molecular effects. And so there's not an evident path to dissipation. Now, there, of course, are vertical boundary layers. They're volumetrically a small fraction of the flow. I want to talk today about an interior route to dissipation that makes this connection and confounds the Charney argument. And it essentially has to go through a regime that I've here sort of indicated in a specific way by frontogenetic processes, which is one of the most efficient ways this can happen, in which the diagnostic force balances are broken and forward energy cascades, exciting intermediate scales, and then on down through stratified turbulence, through its isotropization to small scale turbulence. Now, the story that I want to focus on starts on the oceanic mesoscale, which is arises from instability of the persistent large-scale currents. And this is a map. It's a sort of more modern map of a similar map from the same person that Peter Rhine showed yesterday of the surface geostrophic eddy kinetic energy. Eddies are ubiquitous but non-uniform. This is nicely plotted on a logarithmic scale, so that you can see the sort of non-trivial levels of eddy energy, even in the relatively quiet regions. And there essentially is no question of where this energy comes from, but the question I want to focus on today is where does it go to? And the start of the story is what happens to mesoscale eddies, how do they lose their energy, and ultimately then what sets their level of energy given the excitation by planetary scale instability. This is a satellite picture of sea surface temperature in about a 300 kilometer squared box. You see on the broader scale, cold and warm on the mesoscale. That is, this is about 100 kilometers. But you also see sharp edges, fronts, and you see wrinklings of those edges, frontal instabilities. These are down on scales of kilometers or tens of kilometers, It's not often one has viewing conditions as good as this one, but it certainly is an indication that there is an active submesoscale process, and I'm going to generically use that term for things on a somewhat smaller scale that are fed by some kind of breakdown of the mesoscale balance dynamics, and essentially fronts their instabilities and coherent vortices that, for example, occur as roll-up of instabilities. I want to focus on two idealized problems whose solutions I'm going to show you, computational, of course. This is turbulence. One, perhaps the simplest, is a way of posing Eddy's flow, uniform vertical shear, uniform vertical stratification, uniform rotation, which was a proving ground for baroclinic instability as a conception of mid-latitude storms. But you can pose it as a problem of turbulent equilibrium if you somewhat artificially have maintenance restoring effects towards this state, whose instability then transfers energy into eddy fields and subsequent turbulence. A related problem is if you have an eastern boundary with equatorward wind, as is typical of all the subtropical zones of the world's oceans, then you will generate upwelling circulation, offshore Ekman flow being replaced by colder, deeper water coming up. That sets up a vertically sheared alongshore current system, equatorward surface current, poleward undercurrent. That's baroclinically unstable, much in the same way Eddy's flow is unstable. And it too gives rise to eddies. And so the general storyline is general circulation instability, mesoscale eddies, but then forward cascade down into submesoscale fronts, etc. Now these two flows are rather different. This one, for example, has a well-defined thermocline and an active surface turbulent boundary layer. This one is a much more uniform, simpler flow, and yet the essential phenomenology is the same. There is, just to foreshadow a final topic, an interesting sensitivity to how deep the thermocline is, as to what the nature of the submesoscale regime is. And so summertime flows with shallow thermoclines and shallow boundary layers are somewhat different in their structure than our deeper boundary layers. But let's postpone that for now. So this is an experimental result from the idealized eastern boundary current, constructing a horizontal wave number spectrum of the surface kinetic energy, and the different colors are a sequence of solutions at progressively finer horizontal resolution. So this is just a particular computational experimental path to seeing what happens when you open up the resolution range into the submesoscale. And the solutions here are going from ones with a horizontal scale of about 12 kilometers to less than a kilometer. The mesoscale is typically associated with the first baroclinic deformation radius, scale of the order of 50 kilometers. This spectrum peak is the mesoscale peak. With this particular posing, the mesoscale statistically is not changing very much with resolution, but you clearly are opening up a range of smaller scales, and you're doing so in some way that is asymptotically approaching something like a saturated spectrum shape within the dissipation range moving farther out in scale. There are three comparison lines here, not to make too much of spectral numerology, spectral slope numerology. This is the -3 slope that Charney's geostrophic turbulent forward entropy cascade range would predict. It's clearly far too steep for these results. This is a -5/3 range, which of course we always look for, and there is a rational model called surface geostrophic dynamics that in fact gives that -5/3 range for this quantity. But these spectra are steeper than that, at least by a bit, and the best fit is essentially a -2. And so one has the sense that one isn't looking at these particular types of regime, it's something else. If you go into measurements, this is actually an experimentally very well determined quantity. This is a composite data set analysis from driving a ship around the Pacific Ocean forever and ever and ever. And you see near surface temperature variance spectra as a function of horizontal wave number, and near surface horizontal velocity spectra, kinetic energy spectra. For sampling regions, the velocity spectrum cannot be carried to such fine scales, but this is a pretty clear -2. It's certainly not -3, and it's actually in this case, because the scale range is large, it's pretty clearly not -5/3. And there's prior indication of this. Actually, the spectral estimation from the distribution of surface chlorophyll has an older history, and it too is known to be essentially a k to the -2 in sort of broad quasi-homogeneous regions. So whatever, there is then a coincidence by this spectral indicator of these regimes. And so what's going on, let's just look at a series of flow visualizations, snapshots in this idealized eastern boundary current. This is a instantaneous snapshot of the sea surface, a height that is the dynamic height. So if you think geostrophically, this provides the contours around which the flow circulates. And you see in this particular 600 by 600 display something that is on the mesoscale. These are the mesoscale eddies. That looks to be mostly what's there, although you get a hint that you wish somebody would focus the image slightly. But in fact, this is well focused. There's a little small scale blurring around the mesoscale structure. There's a very interesting observational question in oceanography with high resolution satellite altimeters that may be flown, because they would like to take measurements of seafloor surface height on rather small spatial scales and turn them into diagnostic analyses of near surface velocity using geostrophic relations. And so one can ask how well that might work in such a regime as this. This, for the same place and time, is a snapshot of the sea surface temperature. You see the mesoscale. You actually see some of the larger mean scale of the cold near boundary upwelling in the warmer offshore waters. But you also now start to see sharp gradients in a way that is not so apparent in the sea surface height, and you start to see a substructure here that looks mostly like fronts and frontal instabilities. If you take that same situation and depict it as the normalized vertical vorticity, surface vorticity field, then you again see your mesoscale. You see your mesoscale by, for example, the center of the eddies being places in which the amplitude seems rather small, as if by this measure not much is going on, and yet this is what dominates the altimetric measurements. But the center of this eddy is a small Rossby number. This is in effect a Rossby number core. And there are other eddy centers, but in the eddy margins, there's a very active, much larger vorticity signal on a much smaller scale. At times, in places, it looks sort of long and straight. You see indications like this where there was something long and straight that looks like it's had roll-up vortex instability. The soil being is compressed into vortices. And so the characterization is that fronts are being made between the eddies. The fronts are often unstable. The frontogenesis itself generates strong, mostly cyclonic vorticity. We can connect to yesterday's stories. We don't see, I actually cut off the color scale here, but there isn't much strong negative vorticity because of centrifugal instability. coherent vortices that are created by the late stages of this frontal instability. Finally, if on a somewhat zoomed scale horizontally, this is maybe half the size of the previous domains, we look at two other fields, namely the surface density gradient, where clearly you have quite sharp fronts that are sparsely distributed, and sometimes those fronts are quite well formed and straight, as if stable, and sometimes they are indicative of an active instability process. If you look at the vertical vorticity, you see vertical velocity, you see coincidence of the strong vertical motions with the strong density gradients, and you often see this two-ribbon structure of orange-blue, up-down on the two sides of the front, and that's a sign of active frontogenesis going on. I'll show you a sort of process cartoon of frontogenesis in a moment. It's easier to see in the probability density functions. Here are the two of the near surface fields I've showed you. One is the normalized vertical vorticity. This is the -1 to 1 range. That is, nominally, this is the centrifugal instability limit. There's some spillover to it. But in particular, the cyclonic tail is very much stronger than the anticyclonic tail. So the surface processes in the submesoscale here are creating primarily cyclonic vorticity. And in terms of vertical velocity, there's a strong skewness towards downwelling, strong downwelling going away from the boundary. By mass continuity, there's as much upwelling, but it's more broadly distributed, and so it's not as intense. Now, the sort of idealized characterization of this process is something that the meteorologists have been broadly comfortable with for a long time. Atmospheric fronts are palpable phenomena. The big difference is that fronts are rare events in a meteorological world. When one comes through, it rains. There's maybe one front per storm, or at least the one front they like to talk about. There are 5 storms around the world at once. Whereas for various reasons of various scales, this kind of regime I'm talking about is full of fronts, and many fronts per eddy sometimes. And so the frontogenesis is in that sense a more ubiquitous process, and very much in the picture I'm trying to paint part of the turbulent cascade cycle, not just a distinguished event on a weather map. But the essential process is that given a horizontal temperature gradient, horizontal density gradient, let's assume along axis symmetry, there will be a geostrophically balanced along front flow. And if in addition it is in the presence of a pure strain field, a deformation field, with the axis aligned the way that I've depicted it here compared to the confluence of the deformation field, then you will have a strong frontal sharpening. And in fact, the rate of that occurring, even in the surface geostrophic model, which is sort of the least exciting model dynamically, it is exponential in the deformation rate. That is, the front proceeds as e to the alpha t, where alpha is the strain rate of this flow. And in the process, you spin up a secondary circulation. Here's the 2 ribbons in W, up on one side, the light side down on the other. Because of the convergence that's happening near the surface in this flow being strongly across the front at the center and then slowing down on this side, you're in fact further accelerating the frontogenesis, so your frontal sharpening is super exponential. This is something in which you're acting to restratify, that is, you're raising water in the light region, you're sinking water in the heavy region, so you're converting from potential to kinetic energy, and the vortex stretching here is essentially on the cyclonic side, and this ends up being the dominant sense of relative vorticity. The stretching on this side, sorry, I just spoke backwards. The stretching on this side is the cyclonic side as labeled, and that's also the stronger downwelling side, and so it's the nonlinearity of the frontogenesis with this secondary circulation that's creating the skewness of dominant cyclonic downwelling. And this is what's making the fronts, and it's a very effective way to carry energy into the submesoscale from the mesoscale. This deformation field is to be associated with the mesoscale eddy flows. Now, sort of switching flows, but pretending it's all the same flow. This is into the equilibrium eddy flow, where we have a capability of essentially carrying it to even smaller scales relative to this frontogenesis, and in particular arrive at a scale small enough such that the frontogenesis is arrested. And you're seeing here an example. Top line, a essentially stable front in a horizontal plane, sharp temperature gradient, vertical velocity that is dominated by this up-down secondary circulation structure. And another example of another front that is actively unstable and in fact is being inhibited from further frontogenesis. So at a certain scale, which is not an externally imposed scale, it's a dynamically internally arising scale, frontogenesis will stop and break down to its own instabilities. This particular flow in this particular regime is one in which it's a horizontal shear instability of the front, that the horizontal density gradient, not density, sorry, shear gets to be so large that leads to this particular instability. And these are sites of strong breakdown of gradient wind balance, even more so geostrophic balance, and even to some degree breakdown of hydrostatic balance. So this frontal instability, this frontal arrest, and this loss of balance are coinciding in this situation. You can do what, as far as I know, the meteorologists never did, which is to do a linear instability problem for an actively sharpening front. And this is the result of a particular calculation that is a realization of that cartoon I sketched of a uniform deformation flow and a long axis uniform front. And this is the long axis wave number of the most unstable mode, growth rate sigma, normalized by the deformation radius, at 4 successive times as the front gets sharper and sharper. And you see that as the front sharpens, the scale of the instability decreases, the strength of the growth rate increases, and since this is normalized by the deformation radius, any value of the growth rate greater than 1 means the instability is growing faster than the front, if you take a simple exponential growth characterization of both of them. It's super exponential, but only modestly slow. So, and similarly, this in an evolving frontal flow, this is not precisely an exponential growth, but it's approximately so, particularly if the instability is growing faster than the front is sharpening. It's essentially scaled by what is an initial cross-front width. But of course, with time, that cross-front width is shrinking. And so part of the growth of K is that shrinking of the cross-front scale. Well, I think there are probably several possible instabilities that could limit it. This one is essentially a baroclinic instability, so it's not a Kelvin-Helmholtz instability.
It looked like surface geostrophic dynamics on your small scales. Is that anything in that?
There's something in that, although surface geostrophic dynamics with its uniform interior potential vorticity and its monotone gradient of potential vorticity in the surface density is something that has a Rayleigh stability theorem and so is not unstable.
Okay, but if the temperature is streaky, then it's unstable just to SG as well as everything else.
If you start giving yourself a more complicated cross-frontal profile, yes. But this is a non-SG instability.
It's a great discontinuity.
So what is the frontal slope, say, compared with that further out? Is it shallower or steeper?
You're essentially asking whether the vertical shear or the horizontal shear is dominant, and this kind of behavior happens in both sides of that regime. It can be primarily a barotropic or a baroclinic instability.
It's more than one type of instability.
And then there's centrifugal instability lurking around when you have surface fluxes. There's several.
Instability.
This is, in the regimes that I'm showing you solutions from with the idealized problems chosen for, this is primarily a baroclinic instability. Like everyone else, time is flying. Let me, without bothering to define available potential energy, which is an interesting subject in itself for a non-uniformly stratified finite amplitude fluctuation bounded domain, we did. And this is the result for the Edie flow of spectra and spectral flux. That is, the wave number derivative of this is the transfer function of kinetic energy and available potential energy and kinetic energy spectral flux and available potential energy spectral flux. They are positive, it is forward. They are not strongly varying with wave number. That is, this is something approaching what is called an inertial transfer range within limitations of the realization, if nothing else. The spectrum slopes are close to k to the minus 5/3, at least once you get past the frontal arrest scale, which is about here to the left. It's more the frontal process that I was talking about earlier that is more a k to the minus 2. But there is a coupled forward cascade range below the frontal arrest scale. It in fact has a weak negative conversion from kinetic to potential. It's the reverse of the behavior in the frontogenetic regime. And this phenomenology is rather similar to some solutions that Lindbergh and colleagues have shown for purely stratified non-rotating turbulence. This is still a flow dominated by rotation, but it suggests there's a rather seamless continuity of phenomenology that is possible in the forward cascade out of the geostrophic balanced regime into a more stratified regime en route to a real Helmholtz instability and down to the isotropic regime. Let me, I guess I'll make this the last slide and skip another subject. So this is essentially a summary of the energetics diagram that we can, precisely sort of realize in this Edie flow and qualitatively confirm in other flows like the eastern boundary flow. And I've purposely drawn it to somewhat resemble a famous diagram that Rick Salmon drew for geostrophic turbulence almost 30 years ago. If this is referring to the eddies, this is the available potential energy as a function of scale. This is the kinetic energy. If the eddies are generated by baroclinic instability, then there is a conversion to kinetic energy in the process, and there is some degree of forward cascade, at least down to the first baroclinic deformation radius, conversion to kinetic, and inverse cascade on the larger scales in both potential and kinetic. In these flows, there is in fact a continuity of the forward potential energy cascade through the frontogenesis process. And at some scale approximately coincidence with the frontal arrest scale, the feeding of frontogenetic energy into the kinetic energy reverses from an inverse cascade to a forward cascade, and so you have this dual coupled forward cascade range at smaller scales en route to a finite dissipation, and thus essentially confounding the geostrophic turbulence expectation. And the way that it happens is because even if the larger scales have small Rossby and Froude number, local measures of the relative vorticity over F or the vertical shear over N become order 1 or larger, and so this leads to the breakdown of geostrophic balance. And that essentially leads to a kind of manifesto with a kind of counting of attributed to primitive peoples of 1 to infinity. A couple of solutions here, a few more actually than I've shown, but still not very many. For a situation with a strong energy throughput and away from boundaries, vertical turbulent boundary layers are a special case, then as long as the Reynolds number is large enough that no matter how small the Rossby and Froude numbers are for the spectrum peak scales, that there will be forward cascade by various mechanisms. Frontogenesis is the one I've emphasized, but there are others that can be talked about, achieving flows of order Rossby number order 1 and smaller. And this is somewhat analogous to a similar manifesto that has come out of the stratified turbulence community in recent years, where initially it was argued that there might be inverse cascade in stratified turbulence, but the realization is that with high enough Reynolds number, there indeed is a persistent forward cascade in stratified turbulence until the Froude number by local measure becomes large enough that overturning and transition to isotropization can occur. And these are non-uniform kinds of asymptotics. That is, the flows are developing their own contradictions to the asymptotic scaling assumptions that one can make describing the spectrum peak behavior. And this essentially opens up a pathway from the planetary scale to the small scales for things like diapycnal mixing and dissipation. This is a realm that has largely in the ocean been thought to be attributed mostly to inertia gravity waves. I'm sure there are plenty of inertia gravity waves, but this is also a viable contributing route into the scale regime. Thank you.
Time for a question or two.
Yeah, you insisted on this eastern boundary current, and in the presence of the board of the coast, there are ageostrophic instabilities which are presumably involved in the process you are discussing with us, like Rossby-Kelvin resonances and others. Could you comment on that?
There is certainly the possibility in a linear instability sense for such modes, but in fact the pathway that we see, and we have seen in other flows when you have both ageostrophic instabilities possible and geostrophic ones, is that the geostrophic instabilities have stronger growth rates and dominate, and the real pathway into ageostrophic motions in forward cascade is out of, call them secondary instabilities of the geostrophic eddies, not primary instabilities of the mean flow.
It depends on Rossby number.
No, I don't think it does.
Okay, Michael.
Another of these pathways I don't think I've ever seen discussed, although Jack Whitehead and I, John Marshall, have talked about it a bit. I call it the Dimbo effect, diapycnal mixing by baroclinic overturning, and you've got it in your ED case, Jim, because if you have a surface geostrophic...
If I write down the formula that Breitauer wrote down yesterday, if epsilon is the cascade rate, the energy dissipation rate, or to be precise, it's the scalar, the potential energy cascade rate, and n squared, this is the diapycnal diffusivity that is implied. So forward energy cascade implies diapycnal mixing.
Okay, but you haven't let me finish my point. which is that if you have something like a surface geostrophic baroclinic instability, which I think probably you have, well, of course the original eddy instability is that, what you have is sloping isopycnal surfaces intersecting the boundary and being twisted around by the eddy motion, and that just geometrically produces static instability. And that gives you diapycnal mixing straight away. That's what I call DIMBO.
I don't think you can get there by surface geostrophy.
It's just
Surface geostrophic model has no net forward energy cascade in a volumetric sense. This is something that Hoyer and Soderny showed a long time ago. Forward cascade cannot occur within a surface geostrophic model.
Surface geostrophic assumes it's statically stable. If you think of the kinematics of a sloping isopycnal surface being twisted at the bottom, you will produce statically unstable regions. And that's
I
outside.
believe in that. I just am trying to move it outside the surface geostrophic
Well,
model.
this moves it up. No, that's right. It does move it outside, but the surface geostrophic is what kind of causes it all to happen.
Let's have one last question from Peter.
What is the potential vorticity portrait of this? The eddy model is special in that the PV is concentrated in sheets at the boundary. Garner and Held et al. Had lifted those sheets into the interior, and I'm just curious how the frontal activity
The
at the boundary
eddy problem is essentially
reaches the
one
interior.
that is in potential vorticity as you've described. The eastern boundary problem is not one in which the potential vorticity is confined to the surface. And in particular, there are strong fluxes of potential vorticity into the interior, partly accelerated by frontogenesis. Frontogenesis is a very good aid to potential vorticity injection into the interior. But
So you characterize the spin down as the frontogenesis tends to be concentrated at the boundary, and yet the energy is deep, and yet, so how does the spin down portrait look? It's, if you're the interior baroclinic energy.
if you're working under a constraint of uniform potential vorticity, then you come up with some contortions for explaining some of your baroclinic instability spin down. Of course, the eddy problem has two boundaries, and so it can get around that constraint. The eastern boundary current problem is one with really only one active boundary. The other boundary is so far down it doesn't matter. But in more generic ocean flows, you do have potential vorticity gradients in the interior to work with. You don't have to contort yourself so much to try to fit entirely within a surface geostrophic potential vorticity sheet.
Okay, let's thank